so calculating limit laws. So here we're actually going to start doing stuff algebraically. And so we're going to start calculating limits using algebra, not just looking at graphs. All right, so the following laws allow you just to replace a limit with the actual value. And so here we're going to start with really basic things. So here, the function value, here I'm setting f of x equal to x, right? It's just the really boring function. Oops, I didn't mean to do that. It's just the really boring function of y equals x. Well, if you have this really boring function, the limit of that function is just a. It's kind of obvious, right? But once we state that obviousness, it makes it this. And here we're going to have the function value just equal to c, right? Some constant c. And in this case, we're just going to have it to be -2. So notice here, at any point on this graph, like if I looked here, if I come in from the left and come in from the right, it is just going to be x, whatever that x value is. So here at -1, if I come in from the left and right, it looks like -1. Here at 3, if I come in from the left and come in from the right, it looks like 3. Okay. Here, for this graph, it doesn't matter where I'm coming at, it's always going to look like -2, right? It doesn't matter which value I'm coming close to. Like here, what's the limit at as x approaches 2.5? It's -2, right? I mean, this seems kind of silly, but it allows us to justifiably write some things out, right? What's the limit of e to the third power as x goes to 0? Well, that's just e to the third power. Remember, e is just some constant, and if I cube it, it's still just some number, right? Same thing for here, right? The limit as x goes to 2 of the function 4, well, that's just 4, right? Because if I plugged it in up here, it'd just be a line up here. Now, this is the one that we care a little bit more. I mean, we're going to use all three of these in about 3 seconds, but the limit as x approaches 2 is equal to 2. And so once we have this established, we can start with a whole new set of rules, which will allow us to do something very, very nice. And then everything we taught you in the old classes, we're going to throw away for 5 seconds. It's just how it's going to work. All right, so let's look at this. So limit laws allow you replace with an expression of limits. So these are only valued if the limits of the equation exist. You can represent this, real numbers. So here, let's just do this. So there are a bunch of limit laws. Your book's going to label them 1, 2, 3, and 4, 5, or 6, or whatever. Some of the other notes I've seen, they label them differently. I'm not ever going to ask you what limit law did you type in, right? Just say, I may ask you to show each step, but I'm not going to say this is law blankety blank, right? I'm not going to make you label it. So let's get into what the laws say. So here, if I have the limit of 2 different functions, that's the same thing as the limit of one function plus the limit of the other function. Same thing for negation. If I multiply by a constant of a function, I can pull out that constant. If I multiply 2 functions, if I know if 2 things are multiplied, I can split it up, find the limit of one function, find the limit of the other. Here, for this one, if I have some division, right, and I can say the limit of this is equal to the limit of this, if and only if the limit is not, of the bottom is not 0. If the limit of bottom is 0, you have to do other things, okay? Here, if the limit of a composition is the limit, you can take the limit of one of the functions on the inside and then produce this. This one's a little bit wonky. We won't use it that much. And then here it says if it is an open interval where 2 limits are, if the 2 functions are the same and then their limits are the same, provided they exist. We'll use this one. And so these are just all the rules you're allowed to do. And so now we're going to take this limit, not by graphing it, but actually just by computing something. So here, according to my limit laws, if you're going to have to write down each step, so here I have the limit as x approaches -2 of 3x squared minus the limit as x approaches -2. Let me make that look like a -2 of 5x plus the limit of x approaches -2 of 4. So here we're just using the first two laws here. I can add and subtract limits, and so I can do this. The second thing I need to do is now I just need to split it all apart, right? So this is equal to the, let me just leave myself limit as x approaches minus 2. And so this will be a 3 times the limit as x approaches minus 2 of x times the limit. We're only going to get this pedantic, and pedantic means overly detailed during this section. Oops, minus the limit as x approaches minus 2 of 5 of the limit of x approaches minus 2 of x plus the limit as x approaches minus 2 of 4. Okay, now what are we allowed to say? Well, I'm allowed to say this is negative 2, right? I'm allowed to say that now. I'm allowed to say this is negative 2 because of our earlier limit law, right? I'm allowed to say this is 3. I should have left myself a little bit more room. Minus the quantity of negative 2, or oops, this is 5, according to this law, right? Times minus 2 plus 4. So what is this all together? You know, I don't actually have the answer in front of me. Let me calculate it real quick. This is positive 4, so 12 minus, so 12 plus 10. I think so, yeah, 12 plus 10 plus 4 should give me 26. Plus 26. Let me double check this in a calculator. I got 26 too. Good old calculators. Hi. I don't need to take the limit right now. I just need to figure out what 3 times minus 2, because I have a terrible history while teaching to not be able to do basic math. At 26. Okay. And so here we figured out what the limit is. The limit here is 26. Now what laws did we use? Well, we use this law right here. We use this law right here. We use this law right here, and we use this law right here. And so we use most of the laws. Now the nice thing, if it's a polynomial or a rational function with where a is in the domain of f, right? You can just say the limit of x approaches a for this, for all polynomials and rational functions. So we did it once, we don't have to really do it again. Okay. All right, so let's go ahead and do the next set of notes. All right, so let's actually crunch through some numbers then.
Then I have a quick question.
Go for it.
So it's only gonna equal itself when it's x approaching -2, right?
No, it equals it. So limit of x, let me go back to here. The limit of x equal to a, of the limit of x of a is for whatever value I put in here.
Oh,
So if
okay.
I put in -2 in this and this. In this case, it's -2, and that works out fine. In fact, but once we've done it for -2, we're just going to extend, well, this was going to be true for any limit I take. So if I put in 10 here, like so limit of 10, the only thing that changes here is I'll change these -2's out for 10's, right? And then I'll get a limit and I can calculate what that limit was, just by direct computation, right? So direct computation works. So if it's a polynomial, you can just, what they call it, it's the limit by calculating. You just calculate the limit by just plugging it in. You just plug it into the value and pop out what the answer is. Okay. We call that direct substitution, right? You just directly substitute in and it works because of these laws. And we had to show this once. The next thing we're going to do is here. Let's talk about these two real quick. All right, so here we're going to use algebraically to calculate this limit. Now, is -4 in its domain of this? Where's my cheat sheet for this page? I made myself cheat sheets on purpose. There it is. All right. Is -4 in the domain here? Or is +4 in this domain, if the actual function? Yes? No? Maybe? What happens if I plug that in? Let's test it real quick. You're probably right. What isn't in the domain of this function? What is the domain of this function real quick? What is the domain? Do you guys know? Well, here we can figure it out together. Here we have to have x squared minus 7x plus 12 is not equal to 0, right? Because that's what we need. We'll factor this. So we'll have x minus 3, x minus 4 equal to, cannot equal to 0. That means x cannot equal 4 or 3. So is 4 in the domain of this function? No. So 4 is not in the domain here, so I can't directly plug it in. Now, this might seem crazy, but what you're allowed to do is, and so here, we couldn't just plug this in and get a value, right? We just can't. And let's graph this super fast, because we have a little bit of time, and I do want to graph this super fast. So let's just graph this super fast. So let's just go from here. Let's graph this. So let's graph, this is x minus 4 divided by, oops, sorry. I know I wouldn't be on that line. We have x minus 4 divided by the quantity of x squared minus 7x minus 12. No, plus 12? Plus 12. All right. So here we're at 4, right? This value actually doesn't exist, because here if I took this, plug this into Wolfram Alpha, that is not what I wanted. That did not. 4 minus 4 of 4 squared minus 7 minus 4 plus 12. This should give us a bunch of unhappiness, right? It should yell at us. It's undefined, right? So this is not in. However, what you're actually going to do is you're going to take the limit as x approaches 4. And then here we're going to say x minus 4, and then we're going to go and factor the bottom. X minus 4, x minus 3. All right. Now, before, you were not allowed to do this, right? You could not do that because you cannot multiply, you cannot add or divide or get rid of zeros. You just weren't allowed to do it, right? Oh, the graph's on. Oh, this is what we did before, right? This should look excessively familiar. Hi. I'm all graphing it fancy. Hi, what's this? This is our happy graph, remember? Right? This is the one we did before. I'm all graphing it fancily, and we already had it. Thank you. All right, so we cannot do this, right? Because we cannot throw away a 0 on the top and bottom. We were not allowed to do that. But are we ever actually 0 in this case? In this case, we're never 0. We're only close to 0. We're actually really close to making, so this, while this number approaches 0, it never really is 0. So we're actually allowed to do this now. Now we're allowed to do this. And so here, this is the same thing as saying the limit as x approaches 4 of 1 over x plus x minus 3, right? So these are actually the same limit. And the reason we can say that, instead of writing it that way, hold on, let's write it this way. And so using our limit laws, we can actually say this, because we're not actually dividing a 0 over a 0. It's not actually what's happening because we're never at 4. The limit doesn't care, right? You couldn't do this if you're doing normal math, but if you're doing limits, you're allowed to divide out the zeros. You're allowed to divide zeros. You're allowed to do a lot of stuff because you're not really dividing zero because this is really arbitrarily close to zero, but never zero. Does that make sense a little bit? Once we get here, we can just directly substitute, right? Now this is in the domain of this, right? And then we can apply this rule here, right? It's in the domain now. So after just a little bit of algebra, we can apply the domain law. And so this is just equal to 1 over 4 minus 3, which is equal to 1 over 1, which is equal to 1, which we know is the answer. We already calculated it, right, from the last section. Same thing happens here, right? The same thing happens here. Is the limit, and the point of this page is just to get you used to the fact that you can ignore things that you weren't allowed to ignore before. So the limit of g of x as x approaches 1 is actually equal to the limit of x plus 1, right? Do I actually care what the actual value is? No. The limit actually never looks at the value itself. Remember from the other page, as we walk into it, the limit doesn't care, right? The limit only cares about values arbitrarily close to it. So we only care about this part of it, and we just kind of ignore this part. And so for this limit, it's 1 plus 1, because here I can just directly substitute in, because this is a polynomial, and I get a 2. Okay? How do we know this is when this is applicable? Because when equals 0. So if you plug it in straight away and you get a 0, or you get it outside of its domain, see if you can do some algebra. And since you're canceling things, before you couldn't cancel this, right? Because such a thing cannot exist, right? Such a thing can't exist. You can't have x equal minus 4 because then you'd have a 0 and then you'd have huge problems, right? You just weren't allowed to mess with it as much, right? Because this function is not equal to this function. These two functions are not equal to each other, right? However, for the limit, you're allowed to do it. And I guess that's the only thing I'm trying to get here is like kind of forget the rules that we kind of skated around anyways and allow yourself to do the things that you weren't supposed to do. So here, we're canceling a 0. You weren't allowed to do that before, but now you can. Here, since we're arbitrarily close to a number, we actually don't care what the value is. This graph is just going to look like this, right? And let's just say real quick, just for the sake of fun argument, let's just do the limit of h of x as x plus 1 if x is not equal to 1, and pi if x is equal to 1. Well, what's the limit as x approaches 1 of h of x? Does anyone know? What's this limit? We have a vote for pi. We have a vote for anything else? Do we care what the actual value is? Do we care what the actual value is? No, we don't care what the actual value is. We just care what it looks like arbitrarily close to it. And so here, once again, this would actually follow the same thing here, and this ends up being 2. Okay, so limit. I get this is hard because limits we're going to try to break you of all the things that you're used to doing, right? And so it's kind of a new mode of thinking. The calculus itself isn't terribly hard. It's just a complete mental shift. And until you get that mental shift in, it's why they teach us what we were taught before. They teach you because it was true before limits, right? And then after limits, we break the rules. And then I was in my high-end engineering class earlier this week, and someone's like, is that really undefined, or you guys define it later? And it's like, we define it later, guys. I'm not going to lie to you. We do an isomorphic injection into a different space. And they go, and they just get upset. You're like, well, why would they teach us that? Because, I don't know, you just learn stuff in order, right? You know, I don't know why math, because if we taught you all the rules at once, you'd just be overwhelmed. You'd be like, I don't understand any of it. So let's just finish our last 3 pages. We have about, so we've been going at a decent clip, so I'm not worried actually about finishing it now, which is good. And I'm not worried about rushing too much, which is also good. All right, so let's do that. Let's just put in the last 3 pages. Let's go ahead and clear this out. Apparently 3 seems to be the magic number of things working well. All right, so that's the last page. We'll do that later. So let's do this. And we'll go ahead and get rid of this. All right. I forgot to add one little note in my box. So let me add that with you guys. There's my note from my box. Notes there, and then I got them all out of order. There it is. All right, so let's zoom on in. All right, so there's a couple more laws here. So here, if we take the limit of a function, we raise that function to the power n. I can just take the limit of the function to a and then raise that to the power of n. And here we can do the square root too. However, for the square root, there is a tiny, tiny little caveat. F of x has to be greater than 0. Okay, if f of x is less than 0, I can't just take the limit and do what I'm doing here. And that actually comes into play here. So let's calculate this limit algebraically. Well, here, if I try to do this, here I'll take the limit as, if I just plug it in, right? So let's just take the limit of, here we'll take the square root of the limit of x approaches 5 of t squared minus t minus 20, right? So we're just applying this rule right here. Now, once I've done this rule, I'm allowed to, so this limit is equal to this, right? Because I'm just applying the rule where I put the limit inside the radical. Now, the question is, was that okay, right? Was the limit here? Oops, I have the wrong letter. Let me be very, very careful here. What is the limit as x approaches 5? So go ahead and do this real quick and tell me what this is. If I pull up something for you guys. What's the limit of the inside the radical? What's the limit as t squared minus t plus from minus 20? Where is that limit law? I want to make sure I'm writing this 100% correctly. Now I failed at doing it twice. Yes, it's the limit of x approaches a. So this limit has to be greater than 0 for this to work. Okay. So yeah, the limit is 0. And so here, unfortunately, since this limit is 0, we actually cannot use this, right? We can't use this. And so we just say it doesn't exist, does not exist, right? Okay. And the same reason the limit of, since this is 0, right? Since this is equal to 0, we say it does not exist, right? Since this equals to 0, we say it doesn't exist. Same thing, the reason is, what's the limit of, it's the same reason for this. What's the limit of, as x approaches 0 of the square root of x, right? We saw this before. It doesn't exist, right? So this is the same reason here. Okay, now let's actually look at that graph for a second. And this one I had pre-prepped. Let's pre-prep the pre-prep graph. Whee! Let's go back to Desmos. Here's the one I had saved for us, and ta-da! Let me zoom out and put this back at a normal thing. So here's that graph, right? And here graphically we can see at 5, well, it exists at 5 and it goes off to infinity. The limit here doesn't really exist. Or at least in the traditional sense, because I have no definition on this side. There's nothing defined here, right? So, how is it 0? Oh, here we can use the direct approach. Here we can use the direct approach. Since this is a polynomial, I can just plug in 5. Okay? So here we just plug in 5. So we get 25 minus 5, which is 20. 20 minus 20 is 0. And so we get 0. All right, so this doesn't exist, but what about this? All right, so what about this one? And here, if we look here at the graph of this, we're going to assume this exists, right? I mean, from the graph, what does it look like the limit is equal to? Just real quick from this graph. It looks like it's 3, right? So it looks like it's 3, but how are we going to show that algebraically? So here, we're going to do the same thing we did before, as we're going to pull the limit on the inside. So here, this is the limit as t approaches 5 of t squared minus t minus 20 all over t minus 5. Now, can I plug this directly in? Oops, that looks more like an 8 than a 5. I'll go back right on the right layer, which I was not doing. 5. So can I plug this directly in? And the answer is no, 5 is not, right? This doesn't work, right? However, we can say this is equal to the limit of t minus the 5 of t minus 5 t plus 4 all over t minus 5. So I can do that. Then, since we're not actually 0 here, we're not actually 0 here, I'm allowed to cancel those two, which is something I'm allowed to do. And so here I'll have just t plus 4. Now, is 5 in the domain of this function? And the answer is yes, right? And so this is just equal to, well, this limit here equals 9. So we'll just plug in a 9 here. And so here we get 3. Okay. Why does the limit move inside the square root? Okay, so here, we're using this limit law right here. So here, the limit's outside the square root. We can stuff it in a square root or a cube root or a quartic root. It's allowed to be done as long as the limit's greater than 0, as long as the limit's strictly greater than 0. Here we did the thing not knowing we're allowed to do it, but once we figured out this is 0, we understood, oops, we couldn't do that, right? And so we just said, doesn't exist, right? Here, we plugged it in. We couldn't just plug it in, so we did some algebra and canceled stuff. Now we plugged it in. Is 9 greater than 0? Yes, 9 is strictly greater than 0. Therefore, it was fine, and we get 3. Okay. All right, let's do 2 more, and then I'll show you squeeze theorem, and we'll call it good. All right, so let's look at some other things that just may appear on the limits. All right, so here, can I plug in 0 directly? No, right? Because 0 is definitely not in this, right? And so in order to do this, we're just going to have to do some manipulation. So I'll give you a hint what we're going to do. So here, this limit, we're going to actually multiply. And here we're going to do something absolutely terrible, right? Because here, h approaches 0. But is h actually 0? No. But we want to just clear out we'll just clear this out up top, right? And in order to do that, you're just going to multiply by its conjugate. 1 plus h. Oops. So, oops, hold on, I'm on the wrong layer. So 90% of the time, if you see this, you plug it in, it doesn't work. Just go ahead and multiply by the conjugate, and then it will work. Okay. And this is called the radical conjugate, where you just switch this for a positive. Now, if I do this, I don't need this. Now, if I do this, I'll have the limit as h approaches 0 of this times this gives me 1 plus h. This will give me positive h, square root of 1 plus h. This will give me negative 1 plus h, so that cancels out. And then I get negative 1 times 1, which is minus 1, all over h times the square root of 1 plus h plus 1. Okay. Well, notice that this cancels with this, and this h cancels with this h. And I can do that because h approaches 0, but is not actually 0. I'm left here with the limit as h approaches 0 of 1 over the square root of 1 plus h plus 1. H plus n. Now here, I can directly put it in, right? Here I can directly put it in. Technically, I'd have to stuff this in here and write, well, let me do the technical stuff, I guess, of the square root of the limit as h approaches 0 of h plus 1 plus 1. So technically, I need to stuff this in here. I'm allowed to do that. And then here, this evaluates to 1, and so this just says 1 over 1 plus 1, which is equal to 1 over 2, which is the answer. Okay. So here's just how I do something algebraic. This is a little bit more, this one's a little bit more complex. I mean, technically, I should have done one more step if I was going to be horribly pedantic, but since we're real short on time, let's skip it. All right, let's do this one. Can I plug in pi over 2? No, cosine of pi over 2 is 0, so I'm not allowed to do that. But what I am allowed to do is cancel. And that's what you're going to find out to be true for most of these problems. You're just going to do some arithmetic and cancel. So sine of 2 theta, or is equal to 2, sine, or in this case t, sine of 2t is equal to sine of t cosine of t. And these are just, this is just some sine law that you've learned at some point, hopefully. Here, I can safely cancel the 2 cosine t's, and then here I'm left with the limit of 2 sine of t as t approaches pi over 2. Well, that's equal to 1, so this is equal to 2. Okay. All right, I'm going to get a drink. We might go like 2 minutes over so I can explain the last part. All right, I'll go back to this page if you want to rewrite it down after I finish the notes. I want to finish as close to as on time as possible for you guys, and yet still complete everything I wanted to go over. All right, so I'm going to talk about something real quick. This is called the squeeze theorem. So if I have a function which is strictly less than g of x and a function that's strictly greater than g of x, I'm going to say if I know what the two functions are and they agree with something, I can say then that function is the same. Okay, so let me show you this in Desmos really quick, because if I don't show you in Desmos, you're going to be completely lost what I'm doing. And then I'm going to show you algebraically how we achieve it. Okay, so we are going to go like 4 minutes over. I am sorry about that. So let's just type in, no, let's do it. Let's do it algebraically first. That way you completed your notes, and then I'll show you. And then I'll show you if you have time afterwards. So here, so in order to do these, 90% of the time it's a trig function. So we're going to look at the sine of 1 over x. So sine of 1 over x gives us trouble. It's the same thing as sine of pi over x. It just infinitely oscillates, right? It just infinitely oscillates, gives us trouble. And so I don't know what that limit is, and so I can't split this apart and do it. But I know sine of 1 over x is strictly less than 1, and I know it's strictly, or not strictly, but it's less than or equal to 1, and it's got to be greater than or equal to -1. I know this, right? That's a safe assumption to make, because sine only can give values between -1 and 1. Then I can also say that x, and then I can just multiply everything by x squared. Because x squared is a positive value. It has to be positive. It could be 0 or it could be positive. So if I multiply everything by a positive value here, I won't have to change any of my signs. And so I'm left with this. Well, what's the limit as this? And now let's just take the limit of everything. X goes to 0 of x squared. So what I've done here is I'm saying that this is my function. So here I'm saying this is, to be very clear, this is my f of x. This is my h of x. And that sine x squared of 1 over sine of x is strictly between these two, right? However, I know what the limit is this if this goes to 0, right? And I know what this limit is. So what's this limit as this goes to 0? Well, it's 0, right? I can just strictly plug it in. What's the limit of this as it goes to 0? Of x squared? Well, it's also 0, right? So here, I can say safely that since this is 0, this is 0, that this safely, the limit of this goes to, according to this, right? Here, this goes to 0, this goes to 0. Therefore, this implies the limit of x squared sine of x over x as x goes to 0 goes to 0. Let me show you that. Let me show you that real quick, and then we'll be done. And I'm only 1 minute over, so let's make it only 2. Trust me, squeeze theorem is one of those things that if you see it without working through one or twice, you'll just be unhappy with life. All right, so let's just type in minus x squared real quick. Let's type in positive x squared. And then we're going to type in x squared times sine of 1 over x. Oops, nope, I wanted 1 over x. There we go. All right, so let's kind of look closely into this. Let's get really close. So here, this is strictly, it comes up, it touches this, comes down, comes up, and comes down, comes up, comes down, right? But without these two, right, without these two functions, as more I zoom in on this, it's still just kind of wavy. I mean, it looks like it's going to 0, but it's still waving too much for us to do that. So we just squeeze it between these two functions. And since I know this goes to 0 and this goes to 0, I can say that this limit goes to 0. And so it's just a way of handling that. Could you explain the sine and cosine? It's just the double angle formula. Just look, Google double angle formula. There's a list of them. Okay. So sine of 2 theta equals sine of 2 times the sine of theta times cosine of theta. Okay. All right. Well, that's the end of the note.